name's Adam Taylor, and today I'm going to talk to you about an agricultural trials robot that we've been developing called Marvelous Marv. And this is actually, this has really been this work's been done in partnership with Edge Impulse and Sony as well. So let's take a look at actually what it is and what Marv is and how we use it. So an agricultural, agriculture, we're seeing a lot of moving there for roboticization and the use of AI and such like. My friends at Robotic Farming Systems Limited, they've been working on a agricultural robot, but as opposed to actually doing the picking or the sorting of crops or the removal of weeds, actually it's a dedicated trials robot. And what that means is it's really for crop trials, which is to monitor new crops and see how they grow and make sure that they're given the correct sort of irrigation and spraying. But also, this robot it can actually identify individual crops throughout their growth cycle and actually tag it and monitor them. So this is Marv. You can see Marv there. You can see Aaron in the background. So this is Marv without the cover over it. Normally there's a cover over the over most of the frame, and you can see the sprayers, and you can see the distribution nodules pointing down. So Marv actually has two modes. When it's working in the field, when it's doing trials, it has a spray mode, which is done at a constant 3 miles per hour, and it also has an imaging mode. And in the imaging mode, actually, accuracy is key. And it's in this mode that it tags and it monitors individual plants. So when it's in this mode, it can go as fast or as slow as it would like, which is going to be important as we talk about it in a little while, and you'll understand a little bit more about why that might be. So let's talk a little bit about first, why might we need Marv? What benefits does Marv bring to the agricultural sector and the benefits? And actually, if you've ever been involved in any crop trials, they're really intensive operations, particularly labor-intensive operations. And they're normally performed in very remote locations because you don't want people to accidentally stumble upon them or accidentally cause any issues there. Or even you don't want any competitors to perhaps stumble across them as well. So these crop trials, they're really intensive operations, and what that means is that you need to record the growth of the crops accurately. You need to provide known levels of irrigation, and you need to be able to help quantify the best growing conditions for the crops. Now that means generally that if you've done it within a within a field or a remote location, that it's difficult to get people and resources to it, and continually get people and resources to it to actually monitor these crops and do this work. So it makes access for the trials team quite difficult. And obviously, if they're managing several sites, it becomes quite difficult for them to get around all the sites quickly and easily. So a dedicated trials robot like Marv, actually what it does, it provides the irrigation and the spraying at known levels, at controlled levels. And it's also able, because we've got an imaging system on there, it can actually accurately identify and geotag each crop as it grows. And then you can have a nice history, a nice record of that crop's progress, of that crop's growth throughout the trial. So obviously, it's not a zero-sum game. There's always some challenges when it comes to working, when it comes to creating robots. We have several as well. The remote locations of these crop trials mean that there are limited charging options, which means that we need to be as power efficient as possible to be able to operate for as long as possible in between charging cycles or battery changes. Again, remote locations, they come with their own challenge in terms of needing communication links, and how do we get the data that is on Marv, or the control information that's on Marv, back to the control center where the trials team are monitoring it. And we can do this via several methods. Marv's designed really to work with satellite communications, to work with 5G communications, or to work with a more local lower WAN type network around a larger farm, a larger trial site, if that's what's desired, to communicate the data back to a gateway that can then be sent back to the control center. So we have energy management challenges. So we have motor drives that we need to control, and they can be as we're moving about at 3 miles an hour, or in our imaging mode. And we also have this tagging of the crops and the identification of the crops using image processing and machine learning. Now that again also brings with it a significant challenge because traditionally, and we're going to talk about why this is not the case on Marv in a minute, but traditionally using high performance image processing, machine learning, it uses very high performance processors which also have a corresponding power draw, which would affect the battery cycle. But as you'll see in a little while, we have a rather unique way of doing this, thanks to working with Sony and with Edge Impulse. So obviously reliability as well. We want to make sure that the remote operation, that this system is as reliable as possible and is not causing any issues at all. And one of the things we want to do with this as well is we want to be able to have prognostics and diagnostics such that we can send the data about the health of the system, the health of the robot, back to the trials team so that they can know that things are going wrong. They can begin to see that perhaps a motor's experiencing an issue or a battery's not charging as perhaps it should, so that they can schedule in the maintenance visits, and you're not waiting for the robot to just fall over and stop working with all the associated impacts that come with it. So prognostics and knowing about this information as it's going to happen is also much more important. And finally, we want to be able to have some accuracy of the measurements. We need very accurate measurements for both the crops and the spraying to make sure that we are an order of magnitude, obviously, better than the current approaches. So the Marv team, I'm going to touch a little bit about the team and just introduce the team here that have been developing. The main two developers here are Aaron and Adrian, and they're both actual farmers as well as engineers. I've known Adrian for maybe 15 years or so now through the space industry, and these guys have, Adrian and Aaron, they've created the system. They've done, as you can see in the pictures, they've done a lot of the welding. They've created the structures. And they've built it, so they're really the driving force behind this application. And where we come in, where Aduvos come in, is we've helped we've helped with the image processing with the AI side of things as well. So that's the Marv team. So these are the three people that are currently working on Marv at the moment. So let's talk about its capabilities for a minute. And as we said earlier on, we're going to have a high quality GPS receiver on there, and that's going to be able to take centimeter level GPS measurements, essentially to ensure that the rover is staying on its path, to ensure that Marv is actually, Marv is on the correct path for the trials path that we need. And that centimeter precision as well will come in when we're tagging, will come in useful when we're capturing images of crops, classifying crops, and tagging them as to location. Obviously, as we've talked before, it's designed to be robotic, to be operated remotely by a LoRaWAN, LTE, 5G, or SATCOM, depending upon the configuration that the end client wants to use it in, whether they have several Marvs working across several trial sites that are reporting back to a central hub where LoRaWAN might be used, or if they've got just one Marv in a remote location and you want to use a 5G or a SATCOM link. One of the main elements, obviously, that Marv can do is Marv comes equipped with a high precision sprayer, such that it can spray and fertilize, and it's really designed to apply this spraying system is really designed to apply specific chemicals as accurately as possible to ensure that we get the best results for the trials. It's a highly targeted, highly efficient system there. We want to also, as we're going along, we want the MarvBot to be able to monitor and record the weather and the soil conditions. So you've got a holistic picture of everything that went off throughout the trials period. So as you've got the best known picture to understand how the crops grow best, or if they're not growing, what factors might have impacted that in terms of growth. So we're going to provide weather and soil monitoring, and that can be, like I say, that can be used with the plant measuring. We also have quite a comprehensive computer vision and machine learning system on there, and that's going to do the individual crop analysis. We're going to do the geotagging of location to enable that through life understanding of the crops. But also, crucially, we're going to use machine learning as well as part of that prognostic system that we were talking about as well, to help us with understand the reliability there and make sure that we can schedule maintenance and not be subjected to the dreaded robot down call. And also Marv can adjust its height to be able to fit the crops. So we can optimize the height depending upon what crops we're growing or where we are in the cycle of the crops to be able to ensure that we get the best image analysis images without actually causing any damage to any of the crops. So let's talk a little bit about Marv now. So you can see we have this nice 3D image there of the robot. You can see we have a distributed processing approach. So we have a central processing which does the overall mission planning, shall we say, for Marv, and the communications management. We have the multiple camera systems which are focused on the crops, which are running across the bottom, and they're looking at the crops. They're taking the images of the crops. They're using machine learning to classify and identify the crops. We also have a smart battery and energy management system. So this again is machine learning based control that's going to look at the charge discharge cycles, look at the wear on the battery, and give us that ability to begin thinking about prognostics and how our batteries are holding up, and just to learn about the operating modes of Marv in different conditions and what battery demands are placed upon it. And then finally, we're going to have a prognostic system on the wheel that's going to look at the wheel system, that's going to use vibration and sound actually to feel the acceleration, the vibration that the wheels are experiencing, to listen to them, to see if there's any, again using machine learning, to see if there's any failures coming or if there's any issues with those wheels. And those systems are currently being developed at the moment. Over the next 6 months, we're going to have a wheel with the appropriate prognostic system running to qualify and quantify and grab that data that's necessary. So we're going to take a distributed processing approach to this, and we're going to take an experience from both sort of Adrian and mine's background, which is predominantly in the military and aerospace and space technology area, and we're going to have a distributed line replaceable unit. So essentially, all these systems are going to be highly modular, highly just connected in by using standard connectivity. So we're going to have each one of these is going to be a standard module that can be easily replaced and switched in, switched out, so that if anything goes wrong on the robot, it's a simple case of take this box out, plug this box in. It's envisaged at the moment that all of our communication is going to be done with the central processing unit over Ethernet, and we'll use power over Ethernet to actually power the various camera systems throughout the robot. And this means that we can have these distributed units working and receiving in commands and working as a most optimal solution that we need for the overall design of the robot and to achieve its mission criteria. So I mentioned about the processing and how we might face issues with elements of the design if we're taking a high current, high demand to do our image processing. And what we've decided after looking at several different cameras, several different options actually, is we've looked at the distributed processing element for the Sony Esperance. And this is a small microprocessor. It's got six M4 cores, which run at 156 megahertz. It gives us 8 megabytes of memory, or 1.5 megabytes of SRAM, and it's also got GNSS capabilities. We don't plan to use it at the moment, but it has them, so that's potentially exciting as well. Now, what's really exciting is additionally we can connect to it a 5 megapixel. We can connect to it a 5 megapixel camera, which is ideal to do that. And there are some new camera developments for the Esperance in development at the moment, which will give it slightly better performance in low light and higher resolutions, which we will also be looking at. We also get the ability to use an SD card, and crucially, we can use the GPIO for provisioning with analog and digital systems, such that if we want to connecting custom design boards, for example, that do power over Ethernet or Ethernet routing, then we can do that and provide that. What makes this really interesting is that the processor is what's called fully depleted silicon on insulator in the technology it's fabricated on. So that makes it really low. That makes it really low power. I mean, it's already low power enough because it's running sort of fairly low speed. It's got fairly medium range sort of M-class performance, but it really gives us that ability to have multiple ones of these in the system and not draw a huge amount of power. Now, how might we run elements on this, and what we're going to run on this is quite interesting, because we're going to use these modules to do the crop identification and the geotagging. We're going to use them to do lens efficiency. So it's no good if we're looking at the crops, but the lens on the crops is obscured by dust, by mud, by water. So we're going to have these to actually determine if the lens is obscured by dirt or mud, and therefore we can clean it or rotate it or do what's necessary to make sure that the lens is clean. Finally, we're going to, as we've talked about in a couple of times, we're going to do this for predictive maintenance on the wheels to detect any issues. And we're going to take a look at the battery management as well and use these to battery management. So we settled on a nice, compact, small, power efficient solution which we can deploy in our system to do this. Now, one of the great things about the Sony and the little M-class processors is you can use them with a framework. So for the last few minutes, we're going to talk about the machine learning applications that we're deploying on there. And we're deploying on there what is called tiny machine learning. So tiny ML, which is really designed to be deployed on microcontroller class processors at the edge. So it's where you've got a small processor that you need to be power efficient, but you still want some machine learning algorithms to be deployed on it. And we can do that. And this comes back to the thing I was telling you at the beginning about when it's in imaging mode. It's not like a self-driving car driving down the road that's got to be running images and processing images hugely fast to work out whether it's going to have a collision or whether it's got to avoid people. It can go at a rate it wants to go at. In fact, probably slower is better in terms of battery life. So if we implementing a machine learning algorithm on the Esperance using edge impulse is what we've done. So let's take a quick look at how we've done this for the crop identification. So we've trained a simple neural network, actually in this case, to be able to tell the difference between three crops, which are sugarcane, wheat, and maize. We do this by putting in a 96 by 96 image into the edge impulse, into edge impulse, which is a web-based, cloud-based, tiny machine learning application. And then once we've done this, we can actually run through and we can extract the images from our crop. So we're not working in the RGB, the color domain, even though the camera's color. We're going to convert it to grayscale. We're going to convert it to grayscale and extract the features from the grayscale image. And then we can actually go through and we can train the neural network on the system and deploy it on the camera to actually get the performance. So this is one of our early models, our model that we're still working on at the moment. But you can see we can tell the difference between maize, sugarcane, and wheat with about a 96% accuracy, which is there's still some room for improvement, but that's still pretty good. And we've got a relatively low loss rate on there. So this gives us a machine learning application that we can deploy. And this is a beauty of Edge Impulse, in that it actually does give us the source code, the libraries that you can just literally take and put on the Sony Esperance. So if we take this machine learning model, we can take a look at what it requires on the camera. And now this is quite interesting, because as Edge Impulse runs, it will give you what it thinks is going to be the RAM usage, the ROM usage, and the latency of the image. So you can see here that we're going to take about 3.3 seconds to classify an image. But as I said earlier on the trials robot, speed's not a problem. We can actually power efficiency really trump speed. So a 3.5 second time is perfectly acceptable. So we can have this solution all nicely deployed in Edge Impulse, and then we can test the results. We can do live tests of results. We can take in images into the Edge Impulse environment, and we can run it through, and we can ask the machine learning model to run through in the cloud and see what it's going to classify it as, and see what it's going to get, what it thinks it actually is, which is really good. But actually what we want to do is we want to try it on the Sony Esperance board. So when you put this on the Sony Esperance board, when you take the C libraries that are provided by Edge Impulse and you run it on the Sony board, what you can see is, again, it comes up with a prediction again, which is very similar to what we had previously, and you can see this time that it's taken about 3.5 3.8 milliseconds. So the estimation of performance that Edge Impulse originally gave us of 3.3 milliseconds, 3.3 seconds, sorry, is not completely out of the box when we do this. So we have a nice solution there that gives us a really nice machine learning solution that allows us to work with Marv and be power efficient. So I'm going to wrap this up now. I'm going to talk a little bit. I'm just going to recap on what we've shown. You know, we've created an agricultural trials robot. We're looking at how we can use LoRaWAN for communication along with other technologies such as satellite and 5G. And we've deployed really power efficient, or are deploying really power efficient machine learning, tiny machine learning at the edge using these tiny little microcontrollers that allow us to monitor the not only the image processing of the application, but also the prognostics on the wheels and the life of the battery. If you'd like to reach out, if you'd like to know more about it, my email's there. But prior to that, thank you for listening and have a great day.